In this video, we will look at analyzing graphs of functions. This is from section 1.5. I wanted to preface this video by letting you know that the examples I'm about to begin with are not exactly as the book begins. So some students like my approach, some students like the way the book does it, but at the end of the day, they're kind of interchangeable. So let me describe it this way. The book goes through and shows you some pictures of graphs, and then you write the answers for domain and range. I'm working the other way. I'm giving you the domain and range, and you're going to provide the graph. So it's literally not that I'm trying to be difficult. It's just I think it helps to see it this way. So it might be wise right now to pause the video, and if you have a hard copy of the text, to just open up to section 1.5 and just read the first 2 pages, if I remember correctly, about domain and range. When you start talking about increasing and decreasing, you can pause there and come back to this video. You could use the e-text. Or if you just don't want to do that, then welcome to my explanation of writing domain and range from a graph. So with no further ado, 1.5, analyzing graphs. And our first objective is to be able to write the domain and range from a graph, or vice versa. Given domain and range, create a graph. So my example is just diving right into it. Create a graph with the given characteristics. By the way, there are many different correct responses. And maybe that's why I like this way so much. In a typical classroom setting, and I know it's not, so maybe I should revert to the book's way. I thought about it. I still want to stick to this. But in a typical classroom setting, this is a great opportunity that I would put students in groups. So you'd be working in a group of 2 or 3, getting to know some different classmates, building some networking connections. Who knows, maybe your future boyfriend or girlfriend, wife, husband, whatever. Hey, even just a friend. Regardless, I'm ranting now. But I would say, all right, here's some characteristics. Can you draw a picture? And then you would kind of share out to the class what you were thinking. But unfortunately, COVID has taken away that experience for us. So as you go through these, I'm going to ask that you seriously give it a pause, get a piece of scrap paper. If you have a whiteboard, grab a whiteboard marker, try them to your side, erase them, maybe. I know not everyone has whiteboards, but a lot of us have a younger brother or sister. Maybe we had it ourselves. Can you sketch a graph that has a domain of 0, 1, and 2 and a range of -1 and 1? And so one thing I want to notice here is my notation. This is not interval notation. It's not anything with parentheses. It's not containing a bracket. We actually have a curly bracket. So this is what we call discrete, meaning it's just countable. It's not continuous. Think of it as like isolated. Let me show you a picture of a discrete graph. Dot, 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 dot. And now I'll show you of a picture of a continuous graph. Right? So it's all connected. So when we have a discrete graph, we can literally just say, all right, what's in our domain here? 1, 2, and 3. How do I know that? Because 1 has a pairing, 2 has a pairing, 3 has a pairing. What are my range values? Maybe 1, 3, and 4. How do I know that? Because I trace back to the y-axis. This ordered pair right there pairs with 1. This one way over here pairs with a y value of 3. And this one was supposed to pair with 4. I know it's a little bit off. But that's my brief review on like domain and range from a graph for discrete graphs, okay? But I'm asking you to work in reverse, and there are many, many, many different answers. So don't chances are what I come up with, you didn't come up with if you tried this on your own, right? But if we have a domain of 0, 1, and 2, I'm going to fall back for a minute on what that means. And from the last lesson, so I'm going to end up erasing this, but I can think of a domain as, all right, 0's coming into this rule, which I don't know what it is. I don't know what the rule is. But the only thing that can come out is either -1 or 1. and because I want this to be a function, they both can't pop out. So my only choices are 1 or -1. And here's where there's like infinite number of answers. I'm going to choose right now to pair it with -1. All right, so I'm going to say 0 pairs with -1. All right, that takes care of this. Now I need 1 to pair with something. Again, I only have 2 choices. And I can either choose -1 or 1. I'm just going to choose 1. So 1, 1. And that takes care of that. Now 2 is coming into the machine. And again, I have a choice, either -1 or 1. I've already used them both, so it really doesn't matter. I could flip a coin and I'll just choose 1. So that's it. Now what I can do, right, is create a graph. 0, -1. That's right here. 1, 1 is about right here. And 2, 1 is about right here. And that's it. Here's one possible answer, one of many, that shows a domain of 0, 1, and 2 and a range of -1 and 1. And it represents a function. Okay. So just to reemphasize, if you think about the x coordinates, we have 0, we have 1, we have 2. Oops, I don't know why I put a comma there. And that's the domain. The domain is the set of possible x's. The range are all your outputs. In this case, we have -1 and 1 and 1. Boom. All right. If it's repeated, you only end up listing it once. That's just something on set notation. Not going to go crazy with that, but so be it. All right. And this is a function because I've showed the function machine approach. Why? Every input has exactly 1 output. Great. How could I tweak this in part B so that this is not a function? And there's many things you could do, all right? But one of them, all right, so let's go back here and think, all right, I want this not to be a function. And again, there's many, many things you can do. So when I input 0, I can make it fail to be a function right now. I could make this fail becoming a function immediately. And maybe I'll do that right now. So I can say 0 outputs both -1 and 1. That's not a function. You can't have 2 outputs. Not mathematics, not a mathematical function. But I'm going to say it did. 0 pairs with -1. 0 pairs with 1. All right. I'll just put other stuff down for 1. 1 has to pair with either -1 or 1. So it doesn't matter at this point. I still just have to want to have a domain. And we'll just say -1. Doesn't really matter. All right. Now when I graph these, oops, 0, -1, about right there. 0, 1, about right there. 1, 1, and 2, -1. Remember, those weren't an issue. These were fine. Right. The issue lies right here. 0 has 2 different outputs. So we can see that. I built it that way. But my main point of this so far, my main point I'm about to say, my secondary points before I say my main point, my secondary points have been like, this is what domain and range are. The domain is the set of x's, the range is a set of y's, and I'm using discrete data right now to build these graphs. But my main point is, how can we tell really quick whether or not a graph is a function? How can we tell whether, if we have a graph, whether we're looking at something that's a function or not? And this might be a reminder to something you've learned in a previous math course called the vertical line test. These 2 points are connected by a vertical line, and it's not because they're on the y-axis. We can move those to other places. For instance, I'll make this fail another way. Maybe I'll come up with I'll come up with an example. I'll redo part B here so that, all right, when 0 comes in, let's make it function. 0 is going to pair with 1. Now, when 1 comes in, we'll make 1 become the bad child, the one where it's not functioning. So 1 is now going to pair with 2 different outputs. And then we'll let 2 be the good child. It doesn't really matter. I'll just choose 1 again. All right, so now if I were to plot these, 0, 1, no big deal. 1, 1, and 1, negative 1. Right. Then we have 2, 1. Now, remember, this was the problem. I purposely made that not function. Now, erase all that. Just look here. Just looking at the graph, I know this entire graph is not a function because there's a vertical line that connects 2 points. All right. And so this is an example, or this is what is now called the vertical line test. If you have a curve or discrete data, doesn't have to be a continuous curve, in the plane, it represents a function if it passes the vertical line test. So what is that specifically? That is if the graph of the curve or discrete data is a function if no vertical line intersects the curve or data more than once. Okay. So think about letters in the alphabet. The letter A. Is the letter A function? So let's draw a graph, and if we were to put A over here, is it a function? And the answer is no. It fails the vertical line test. Multiple places, right there and there. That's one place we could draw a vertical line that intersects the graph more than once. You could do it in other places, but you only have to show it fails. You only have to show one vertical line intersects twice. You could draw this one, boom, boom. Right? So as long as you could show it intersects more than once, then you have shown it fails the vertical line test. However, you say, nope, this is a function because it passes the vertical line test, right? I mean, I get what you're saying. You drew a vertical line that shows it only intersects once, but you have to consider, and here's where it's a little abstract, but bear in there, you have to consider every single vertical line that you could potentially draw. Does any one of them stand the chance of intersecting the graph twice? And, you should be pretty obvious that they are. There is more than one. I showed it. The letter B, the letter C, the letter D, letter E, F, G, H, I, J, K, L, all fail the vertical line test. But I believe the letter M, if you draw it like this, passes the vertical line test. No matter how you draw a vertical line, boom, 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 no matter where you draw one, you're only going to get one intersection. All right, so M, the graph of the letter M, if drawn like this, is a function. Represents a function. Cool. Onwards. Now, for letters C and D, we are looking at continuous intervals. This is not discrete data, but this is continuous intervals. But there are some varieties between letters C and D, all right? The biggest one being in letter D, we have some non-included values. So when I get to letter D, I'll show you, reemphasize exactly what that means. But for right now, Again, this is quite challenging. It's a little bit of a challenge. That's why I like it as group work, but I'll talk us through it. I want to create a graph that has the following domain, 1 through 4, continuous. That means every single number 1 through 4, and that it has to have a range of -2 to 5. Okay, so here's what I'm thinking. It's again thinking. I know 1 is going to be the smallest input into this rule, whatever it is. And I'm just going to go with this. I'm going to pair it with -2. All right. So I'm going to say 1, -2 is an ordered pair on the graph. And I'm going to make the same argument this way, 4, 5. 4, I'm going to force a pair of 5. I don't know what the rule is, but something's converting it to this. All right. Now, watch the cleverness. I'm going to plot 1, -2. And I'll plot the point 4, 5 while that's way off for 1, 2, 3, 4. 1, 2, 3, 4, 5. So if I sketch that, that's about right here. And then check this out. I'm just going to connect them with a line segment. This is one of an infinite number of graphs that meet it. Okay. This is one of an infinite number of graphs that would work. And I'll show you how. So for instance, I've already shown that this point is 1, -2, and that this point up here is 4, 5. Okay. So as we go, how you can find the domain from a graph, right, is kind of think about, all right, see, that's pairing with 1 on the x-axis. And this x-coordinate is pairing all the way down with 4, right? So think about shading to the x-axis, right? Shade to the x-axis. Boom, boom, boom. And shade to the x-axis. So all of this would be shaded. Right? So think, you don't have to do this. Just think in your mind this is what you're doing. So my claim is this is the domain of the graph. Everything from here to here pairs with something. And my justification of that is, like, if you were to say, well, Mr. Rodalowitz or Professor Matt, whatever you want to call me, show me that, let's see, 3 pairs with something. Well, I would say, well, here's 1, here's 2, here's 3. 3 pairs right there. So it pairs with something. What about 3.9? All right, well, here's 4. So 3.9 is right here. So 3.9 is pairing right there, right? And that's my argument. Everything between, including 1 and 4, is paired with something. So they are in our domain. Every single number between 1 and 4 went through the machine and got paired out. And that's my argument there. It's my claim. And you need to buy it. Now, in terms of the range, very similarly, if we look at these y values and kind of think of it as like a highlighted sense, this y coordinate is -2. This y coordinate is -1. This y coordinate is something in between there. And same argument for everything here. So all of these y coordinates are taken care of. So if I shade to the y-axis, if I go from my graph to the y-axis all the way through, all of these y coordinates, and that's my claim, are accounted for. So my range is from -2 to 5. So that's it. That's all I have to say. I don't know what else to say there is about it. Lastly, my graph does represent a function because by my previous argument, it passes the vertical line test. And I'm put too many highlighting things in the way there, so I'm just going to let that go anyways. But I can draw, no matter what vertical line I draw, it never intersects the graph more than once. All right. So check, check, check. All right. Now I mentioned there were infinite other graphs you could draw here, and I'm going to show you another one. And I'm doing this kind of off the cuff, so bear with me. I need to go from 1, 2, 3, 4, and it has to go to -2 to 5. 1, 2, 3, 4, 5. So as long as I have something like this, maybe, again, I said I'm doing off the cuff. Let me go up, curve, down, end right there. Right. Boom. I claim this graph also fits the definition. Again, thinking about highlighting to the x-axis from your curve, and if you're below, then just shade up. Then all of those, that's my argument. Every number, every x value between 1 and 4 has a pairing. And now if I make the same argument towards the y-axis, right? So if I go from my curve and shade to the y-axis, that takes care of that. And then I could go on this way, so on and so on, all the way down to -2 if I drew that carefully. Right, that pairs. So everything in between here pairs with some x, if you will. Right? So those are my range values. Those are the set of outputs that I get. And it does classify as a function because it passes the vertical line test. Only one intersection, no matter how you draw that. Great. So there's infinite answers. I find this section a little bit challenging to teach, and that's especially because I'm not getting a reaction from you guys. So I'm not sure if this is like, whoa, I'm totally lost, or no, I get this. This is wicked easy. I knew this before. In my previous experience, it's kind of exactly that conversation. Some students sit here and say, no, I get it. For the ones who don't get it, then this is like, I try to take the time in class to emphasize this. So if after this lesson you're saying, I didn't get it, then it's probably best that we set up some time to have a mini discussion. That could be a half hour, and I'd like you to email me, say, hey, can we set up a time and go through domain and range from a graph? You're going to need it for calculus. All right. Is it the most important thing to get out of this course? Definitely not. Is it somewhat important? Definitely. All right. It's definitely not the smallest. It's not like the least important. If I said just brush it under the rug, go for it. No, you definitely want to know how to look at a graph and interpret its key features. And one of them is the domain and range. So last rant, if even after I do the next couple examples, it's just not sitting well, let's communicate together. All right. Send me an email. I want you to have success. I literally want everyone to pass this grade. I'd love to see everyone get 100. I hope that comes true. But that's in your court, seriously. But nothing would make me happier than saying everyone got 100 average. So let me know when you need some extra help. I want to help, and we'll figure out a time and a way to get that to you. All right. Letter D. And I'm going to pause. I'm going to stop the video after that example. Oh, no, I'm not. Yes, I am. Anyways, just thinking ahead. Let's do letter D. Can we draw a graph with the domain 1 to 4 and then a range -2, and 0. But I already mentioned this. 4 is technically never seen. We're getting super close, infinitesimally close to 4. So like 3.9, 3.9999, 3.9999. Those are all in our domain, but 4 is not. If I played my game as last time, if I said, all right, let's see. If I take 1 and I pair it with the smallest thing here, I have a problem. I'm saying right here, 1, -2. 1 pairs with -2. It can't pair with -2. Right? We've never seen -2. But I can say, I'll be a little clever. I'll say what I just mentioned here. I'll make it pair with -1.99999999999, and then you can be as obnoxious as you want with that. But I think the idea is set. All right, I'm going to pair 1 with -1.999999999. Super, super, super close to -2. And by the same argument, 4 is never input. I can't input 4. Right? That's what this says. You're not allowed to have 4. But I'm going to pair it with what I can do that's really, 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 really close to 4 is like 3.999999999. And I'll pair that with 0. All right, so that's my ordered pair. Now, if I graph these, I want 1, -1.999999999. Do you know how we show getting really, 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 really close to -2, but not being -2? We use an open circle. We use a dot there, okay? So it's saying like at 1, I'm technically right here, but I'm going to just put an open circle at -2. So I'm going to mark this as 1, -2, but it's really not closed in, right? It's an open circle. So I'm using an open circle to mean I'm get like ridiculously close to it, but it's actually not going to be a point on my graph. 3.9999999, same argument here. Here's 4. So 3.99999999999 is ridiculously close to it. All right. But I'm just going to argue the following. I'm going to say, let me plot the point for 0, but I'm going to use an open dot. I'm not going to close the circle. I'm just going to use an open circle. And then I can connect those with a line segment as a clever solution. There's many ways you can do that, all right? But I claim all the requirements are satisfied. All right, just going through this, hopefully now. Does 1 pair with something? Yes. Does 1.1 pair with something? How about 1.9? How about 2, 2.5, 3, 3.5, 3.8, 3.999? Yeah, all of those have a pairing. So up and 2, but not including 4. Right? So that's what this is showing. So I've met the domain criteria. And by the same argument, I've met the range criteria. I'm pairing with 0, this point right here. I'm pairing with -0.5, -1, -2.5, almost pairing with -2, but I'm using an open circle to represent not a pair. Right? And the book maybe explains this better than I can. Maybe I'm doing an okay job. I don't know. I just feel it's tough for me to explain exactly what's going on. But I like the highlighter way. Right? Anyways, domain and range are met, and what the main point here is that we use an open circle to represent not being included, okay? Infinitely close, but there's actually no output there, right? And similarly, this point right here, we have no output, no input. There's no pairing at all, right? So that's what an open circle represents. And I'll just end this by saying this is a function because it passes the vertical line test at every point along its graph. All right, so that's domain and range from a graph. I'm going to skip the next slide I had there for time's sake and kind of just follow along with the book here. The title of this section is titled Analyzing Graphs of Functions. And so one of the goals that I attempted to do in the first 30 minutes there was write the domain and range from a graph. But I gave you the answers, and we actually drew the graph. I mentioned at the beginning of the video, the book does it the other way. They give you the graph, and you write the domain and range. So definitely check it out. Onwards. When a function changes from increasing to decreasing, or let me rephrase that, the points at which a function changes its increasing, decreasing, or constant behavior are helpful when determining what is called relative minimums and relative maximum values. So first of all, let's talk about increasing. Where is this curve increasing? So graphically, increasing means when we read it from left to right. So as we read it from left to right, the overall behavior is that it's quote unquote going up, right? So as I'm reading this from left to right, if I were to connect those with a perfect line segment, that's going down. But clearly we can say from here, let me use green. Green just seems like a natural increasing color. From here to here, if I connect those everywhere there, and no matter which 2 points I were to connect on that interval, the line segments would always be pointing up, no matter which 2 points you chose. So we say everything from here to here represents an increasing interval. There's another one right here to here, right? Because no matter which 2 points you choose between these, I'll make them kind of bold endpoints here. No matter which 2 points you choose there, any line segment you draw will always have an upward line that connects them. Okay, so that's like the informal definition of what it means to be increasing. So here's our increasing interval. As well as here. By the same argument, when you read a graph from left to right, and if any 2 points on that interval can be connected and have a quote-unquote downward line segment, then it's decreasing. So we can pretty much argue from here to here, we're decreasing. And from, again, here to here, we're also decreasing. And that's a visual definition of what it means to be increasing and decreasing. Now, the bolded words say relative max or min values. When you switch from decreasing to increasing or vice versa, you have either a relative max or a relative min. What's nice is your intuition would probably steer you correct. We call this point right here a relative minimum. As well as this point right here. Min. Right here, we have a relative maximum. So graphically speaking, if you have a turning point, then you probably have a relative max or min. And if you turn from decreasing to increasing, you kind of have like that valley, then you are a relative minimum. But if you go from increasing to decreasing, if you kind of have a peak for a moment, kind of like the top of a mountain, just in that little vicinity, then you are a relative maximum. All right. And that's that. So calculus is going to teach you how to find relative max and mins and the reason why you would want to find them in real life context. So I'll save that for calculus. But I mean, it doesn't take too much to trust that if we had a mathematical way to absolutely find mins and maximums, then things like maximizing profit, minimizing pollution, maximizing healthcare healthcare treatment, and minimizing wasteful spending, or I'm kind of thinking in terms of money, but if you can model some type of situation with a mathematical function, and calculus will provide the way to showing you or giving you how to find maximum and mins, and depending on the context, again, you might want to maximize something, you might want to minimize something. So I'm just leaving that there. For us, we can actually answer it, but without calculus. We can answer like finding relative max and mins using graphing devices such as graphing calculator, which I don't have near me. Actually, I do. I lied. On my phone, I have a graphing calculator. There's an app called Desmos, Desmos, and if you want to download it, you can download it. It's also available to run off a web browser, so you can run it off of Chrome, you can run it off of Safari, you can run it off a laptop, you can run it off a desktop. So you don't need to download an app to access Desmos, but they do have an app. Desmos is a free graphing calculator that I'm going to use in this video to answer the following. Use a graphing device or Desmos.com or a Desmos app to graph the equation y equals negative x cubed plus 2x squared plus 1. So I'm going to share my screen on this tool. I'm going to go to Desmos.com, and kind of went quick there, but just click the graphing calculator link here. I switched to projector mode because it just makes it a little bolder, plus because you're watching on the video. Should help. So I asked you to graph y equals negative x cubed. So to do the exponent of 3, you do shift 6, which is called the upside down caret. Notice my cursor is now blinking in the exponent spot. And notice my cursor is still blinking in the exponent spot, so I need to cursor to the right to get out of it using the little right arrow. And then I can type in plus 2x, again, shift 6 for that upside down caret button, squared, cursor out, oops, typo there. Normal backspace works, and then minus 1. And there you go, you're looking at a graph of that curve. By the way, if you can't access the cubic, or if you're looking for additional functions, in this bottom left corner, there's a keyboard which shows you some of your basic functions. So there's the squared, and if you want to do a power, which is pretty common, you just use the A raised to the B button, type in your 3. Again, you're still going to need to cursor out of it to the right, or you could use this arrow right here, which would do the same thing, plus 2x, and there is a button for squared, so you could just use squared, and then minus 1. That's another way. I point that out, not so much that you can't type it in using the shift 6 feature, but there's also a lot of other features, other types of graphs that we can build using Desmos in the future. So just showing that tool now. All right. Explain why this relation is a function. So why is this pairing, why does this graph represent a function? And your answer here is because it passes the vertical line test. Letter B, and I'm going to switch back to the tablet in just a minute here, but letter B states or asks you to state the domain and range for this graph. So this is slightly deceiving, but it's intentional. And the book does mention this. You might argue, hey, this graph appears to end right here, which is the number -1.5. So you might say the smallest x value I believe that's on this graph is -1/2. And the largest x value is just past 2.5, so maybe 2.6 or 2.7. But it turns out I'm actually wasting my time describing that, because if I zoom out, I can show you that this does go further and further out. It might take you a while to get to 100, but I guarantee you at some point that this graph would cross 100. Now, the book mentions it, and I'm going to mention it here. Unless there's an endpoint on the graph, or you can clearly see it comes to a stop before your graph, it is implied that if there's no arrow here, that we assume that this is going up forever, right? It's just that programs don't have, most programs, even the ones a textbook publisher uses, they don't use programs that put arrows on here. Maybe that's something you can do, become super rich. Just develop a program that creates graphs for textbooks or online texts that have little arrows at the end here to represent going on forever. But if there are none, we assume that it is, okay? So to be honest with you, the domain is all real numbers, right? It does go on and on and on forever. And the same can be said for the range, right? Because I could technically highlight the entire y-axis if I zoom out far enough and far enough. It might take me a long time to zoom out, but it would get there. So I'll leave that as that and switch back to the tablet for a moment here. So I asked us to explain why the relation is a function, because it passes the vertical line test. Totally legit answer. State the domain and range. All real numbers for the domain. I'm just going to say D equals, that represents domain. And the same can be said for the range. For the rest of the questions, let y equal f of x. So I'm just going to say we're dealing with a function. How could you evaluate f of 2 just from the graph? So just using the graph, how could you find f of 2? Then how can you check that your answer is correct? Well, just using the graph, if I look at the graph, how could I find what f of 2 is? Basically, I want to cursor if I like click and hold along the graph, I can trace the graph until I get to x equals 2. And we're there. And I can just say, hey, 2 pairs with -1. So basically, using a graph, I'm just looking for the y coordinate when x is -2. So that's how you evaluate a function using its graph. You don't need to just use the rule and plug in numbers. If you have a graph, go to that x value and take the corresponding y, and that's how you evaluate the function. So f of 2, and I'm reminding myself because I already forgot what it was, f of 2 paired with -1. Now, how could I check that? We can check that using the actual equation, okay? So using the equation, y, again, I'm not calling it y anymore. I'm saying f of 2 is -2 cubed plus 2 times 2 squared minus 1. This makes negative 8. This makes 8. This makes negative 1. So it does confirm it. How could you identify the zeros from the graph? Remind yourself from previous section that a 0 is the x value that outputs a 0. So if we look back at the graph one last time here, and I encourage you to type this in and use Desmos yourself because I'm not going to switch back here anymore. The zeros, what x values output a 0? You should recognize here that the zeros graphically are your x-intercepts. That's literally why I put this on the graph. I wanted you to recognize that we, in previous videos, showed how to find the zeros algebraically, but graphically, you can find the zeros by looking for the x-intercepts. So the x-intercepts on this graph are negative 0.618, 1, and positive 1.618. Those are our zeros from the graph. And I don't think that actually showed up, so I apologize for that. I'm just going to go back to the document. I wanted you to see the graph, but I forgot to switch it back over. Anyhow, I'll leave that to you to check yourself. I guess I will show you because that is important. On the graph, if you click the x-intercepts on Desmos, notice all of these x values output is 0. That's what the definition is. But also notice they are the x-intercepts. So that's an important takeaway or an important connection to make. So we're going to note that. Note zeros are x-intercepts on a function's graph. So that's an important note. Identify the intervals where the graph is increasing and decreasing and state the relative max and mins. I said I wasn't going to switch back over, but I will. So where is this graph decreasing and where is it increasing? I just want to get rid of all this. So we can say it's decreasing from negative infinity up until this turning point. So up until x is 0. And then it's also increasing. I lied. That's decreasing. And then it decreases again from 1.33 to infinity. And it increases on the interval between 0 and 1.33. Right? What is our relative minimum? Our relative min value, or our relative minimum, is the point 0, negative 1. And our relative max is the point 1.333, comma 0.185. Right. And I will switch back here, add this to the stream. So this was decreasing, and this was our increasing. And that's how we write our answers for increasing and decreasing intervals, okay? So just reminding you, we decreased from negative infinity to 0, union 1.333 to infinity. I fixed that symbol. And then it was increasing on 0 to 1.333 on that interval. Just a reminder, because it crossed my mind, these are not ordered pairs. These are intervals, okay? So they're written exactly like ordered pairs, but you know the difference by reading the actual question. Right? That's the only answer I could give you. State the relative max and minimums. These are ordered pairs. These are points where these are turning points. But we're not just saying turning points, we're being more specific. We're saying 1.333, 0.185, that was a relative max. So we know more information than a turning point. We know it's looking something like that. And then our relative min was a turning point, yes, but we have more information. We know it turned from decreasing to increasing. All right. Some definitions. And the passcode for this video, again, there's not one in every video, but I'm decided the second passcode for week 2 is going to be secant. Secant. Passcode number 2 for week 2 is secant. A secant to a curve is the line that passes through 2 points of a curve. Right. So I drew a parabola. I didn't have to. I could draw any curve, but I chose to draw a parabola. And this line that passes through 2 points on the parabola, passes through 2 points, it's called the secant. That's it. It's just a line that can be drawn through 2 points of a curve. Can you draw a secant for another curve? Absolutely. Let's do the square root function. And if you didn't know that, you will really soon. But that's what the graph of the square root function looks like. Can you draw a secant? Sure. Choose a point. Choose another point, connect them with a line, and make it look like a line. Try to use a ruler here really quick. That's a little bit better. But that's it. That's all a secant line is. It connects 2 points along a curve. Sorry, I just smelled burning, but one of my candles that I had lit went out, so didn't want to make sure it wasn't a house fire. All right, so that's what a secant line is. Recall that the slope of a line that passes through 2 points is found by the formula y2 minus y1 divided by the quantity x2 minus x1. That middle kind of fact, you should remember yourself. If not, there it is. But this one might be new, but it's really intimidating. I'm sorry, it's really not intimidating. It just looks intimidating. The average rate of change of a function on an interval is equal to the slope of the secant line passing through it. Passing through the endpoints on that interval. Right? So I'm going to let you read it and digest it, but I'm going to draw one last picture. Suppose I have a curve like this, and I say this is x1 right here, and this is x2 over here in the future. And if I say, what's the average rate of change, which I abbreviate as AROC, of f on x1 to x2, then all you're going to do is follow this formula, but this formula just says you're just calculating the slope of this line that passes through those 2 points. All right. Now, what is the slope formula? It's y2 minus y1. Well, what is y2? Well, y2 is actually f of x2, right? y2, this second y coordinate in function notation is written as f of x2. Similarly, what is this y coordinate? Well, in algebra class, you might call it y1, but in function notation class, or right now, we'll call it f of x1. It's whatever the it's whatever x1 pairs with, okay? But I just want you to recognize this looks intimidating, but it's really just the y coordinates, right? And then the denominator is exactly the x coordinates. Right? So I'm not trying to complicate this. I'm trying to make it make sense, but average rate of change is slope. That's informal, okay? But to be a little more formal, a little more clearer, to justify like what you see in the textbook, I went through and described what a secant line is, which is also our passcode for second passcode of week 2. Reminded you what the slope formula is, and just I'm telling you the definition of average rate of change is the slope of the secant. Let's do an example, and I'm going to end the video a little bit early tonight. I'll finish this tomorrow for the week, but I need to get some rest. Find the average rate of change for f of x equals this function from x1 equals 3 to x2 equals 11. Oh, actually, we're going to finish this video right now. I don't know why I said that. We're only got one more thing to do. So really quickly, average rate of change is f of x2 minus f of x1 divided by x2 minus x1. So we're going to substitute in 11. We're going to substitute in 3. And then we're going to find the difference of 11 and 3. When we substitute in 11, we get the square root of 9, which is 3. We take its opposite and add 5. That becomes 2. When we substitute in 3, we get the square root of 1. We take its opposite and add 5 to it to get 4. And 11 minus 3 is 8. This ratio simplifies to negative 1/4. And that's what we say the average rate of change is. All that means is if you were to sketch the curve, connect those 2 points with a line called a secant line, the slope of that line would be negative 1/4. And we call that the average rate of change. Okay. I said I was going to pause the video, but I forgot. I thought I had a lot more to do. Just this. An even function is a function that is symmetric about the y-axis. So the easiest example I could show you of a graph that's symmetric about the y-axis is a parabola. If you draw a perfect parabola and you were to crease, if you could pick this up, actually draw it on a piece of lined paper, and then crease the paper, then your parabola would overlap itself. So this part right here would overlap this if you held it up to the light. An odd function is said to be symmetric about the origin. What that means, and I didn't understand it till, I don't know, I didn't have a teacher explain it to me, so I had to use the internet back in the day. I still don't understand why it's called symmetric about the origin. I mean, I do, but I feel like we should just rename it, and I'll end my rant there. But basically, what you want to think about is if you were to fold your plane along one axis, so imagine you just, like I did, folded it across the y-axis, but then you fold it again across the other axis, so then again against the x-axis, you would get, then if the two graphs would overlap, that's what it means to be an odd function. So an example of that is x cubed. And again, if you don't remember these shapes, I'm going to show them in the future. But y equals x cubed. If you were to fold this across the y-axis, we know it looks like this. So if you were to crease it along the y, and then if you were to fold that over the x-axis, you can imagine that it would overlap the graph right there. I, again, encourage you to do this on actual paper. So how do we do this algebraically without paper folding or without graph? There is a test. And what you're going to do is the following. You have an even function if you have the following relationship. F of negative x equals f of x. What this says is if we input the opposite of x and we input x, but we get the same outputs, then the function is even. If that is still confusing to you, this is a function machine of an even function. Even would mean this. We take x, it goes through some rule, we get back f of x. We take negative x, so whatever we do here, we take its opposite, we put it through the same rule, and we get the same exact output. That's interesting. I put in two different things. This might be 3. This could be negative 3. But I'm outputting 7 both times. That's what it means to be even. And that's what that says, right? That's what this first rule says. If you input x, you get back f of x. If we input negative x and you also get back f of x, right? If you input this, but you're still getting back that, it's an even function. Similarly, odd means we go to some function, we apply a rule, obviously we get back f of x. Now, if we input the opposite of x, we apply the rule, and we don't get back this, we literally get back the opposite of f of x, then that is what we call an odd function. So to be a little less abstract, again, if we input 3 and we apply some rule, this input 7, then we should input negative 3 and expect to get back negative 7. That's what it means to be odd. That's what that's saying there. So to test whether a function is even, odd, or neither, you're always going to input negative x. That's number 1. All right. So let's do it for letter A. F of negative x is negative x to the 6 minus 2 negative x squared plus 3. Then you're going to simplify. Negative x times negative x times negative n. And 6 copies of negative x multiplied together makes a positive x to the 6th. This next term simplifies to a negative 2x squared, and this becomes a plus 3. So you're going to input negative x and simplify every single time. Now you have to understand the definition. Are you getting back? Are these the same? Because if they're the same, then they're even. If they're opposites, then it's odd. And if it's neither the same or opposites, then it's neither. So looking at these, yes, they are the same. We have an even function. Letter B, start by inputting negative x. So f of negative x is negative x square root of 1 minus negative x squared. All right, simplify what you can. Negative x outside, stuck. 1 minus x squared inside. Okay. Now, I'm going to help you factor out a negative 1. Like take a negative 1, put it out front. If possible. So if possible, going to have times when you can't factor on a -1, but if you can factor on a -1, do it, and I'll explain why. It just helps you to see, look, this expression and this expression are identical. So if we didn't have this darn negative sign, we would be looking at an even function. But we do have this darn negative sign, so guess what? We don't have an even function, but this is opposites. So we are looking at an odd function. Okay. Last but not least, input -x, simplify, that should be minus, my bad. Factor out your -1 if possible. And now look at this. X cubed minus x squared, x cubed minus, oops, I lied. This is a plus. So immediately, these are not equal. These are not opposites. This is an example of a neither. So this function is neither odd or even. And we're going to skip those last two examples there. And that wraps up section 1.5. Okay. I am not doing a video for 1.6, and I was not planning on it. I'm sorry, not 1.6, 1.3. It is titled Linear Equations. And I have the textbook right here. So if you just give me a moment. I actually went through some of this stuff in the 2 lessons tonight. So it's not even 1.3. I'm sorry. Oh, that's calculus. They look the same. Pre-calculus. 1.3. Linear equations in 2 variables. Let me explain what these concepts are. Use slope to graph an equation. I'm sorry, that's a middle school 9th grade skill. You've tested into this course. Even if you forgot the skill, you can look at these examples and learn how to graph a line. Find the slope of a line. Write linear equations in 2 variables. So you might remember something called y equals mx plus b. You might recall something called point slope formula. In any case, on page 26, there's a couple examples done out for you as a reminder. Parallel and perpendicular lines, you should know something about their slopes. And then 1 or 2 modeling questions. How do you use lines to model real world situations? So you can definitely do that review on yourself. If you need additional help with anything, functions, analyzing graphs of functions, and linear equations, please email me. I want to help you. I've said it a few times. I want everyone to be super successful. Have a great semester. I know these videos went a little bit longer than 1 hour 40, so I will keep that in mind for the second part of this week. I did mention last week that we'll try to do 1 hour 40 at the beginning of the week and then 1 hour 40 at the end of the week, but sometimes adjustments are going to have to be made. So I got that in the back of my mind. But to not make this any longer, have a great rest of the week. Your homework assignment is due on Friday. Please pay attention to WebAssign for the dates. And there are 3 sections: functions, analyzing graphs of functions, and linear. I went through every question on there, and I think they're fair for you to answer. And then I'll see everyone on Friday for a virtual lesson. Take care, guys. Email me with questions. Best of luck.